Yeah, thank you. So thanks to the organizers for giving me this opportunity to talk. So I'll be talking about a joint work with Anurag Singh. So for us, binary words are just finite sequences of zeros and ones. So for example, on the screen, you can see a binary word of length 7. A subsequence is a subword you can obtain by choosing some letters in order. So if I choose the second, fourth, fifth, and final letter, I obtain the subsequence 1011. And in this context, we say that the word contains the pattern 1011. Okay. And we'll be interested in how many times a word contains a particular pattern. So for example, this word over here contains the pattern 10 exactly 4 times. And we use this elegant binomial notation to represent this because you can sort of think of it as there are 4 ways to choose 10 as a subsequence of this word. Okay, so the numbers we'll be interested in are of the form B, N, P, K. So here P is a pattern, that is a binary word we'll be looking for as a subsequence. N and K are some integers. And B, N, P, K is the number of words of length N that contain the pattern P exactly K times. Now, before going into the results, I thought I'll mention what motivated us to begin this study, and that is patterns in Grassmannian permutations. So Grassmannian permutations are permutations that have at most one descent. So that means they increase, fall down, and then increase again. And there is a nice way to represent such permutations as binary words in such a way that patterns in the permutations correspond to subsequences in the binary words. So basically the study of patterns in Grassmannian permutations is the same as the study of subsequences of binary words. And this is what motivated us to begin this study. But of course, subsequences in binary words is interesting in its own right as well. Okay, so our first goal will be to compute these numbers B and Pk for small values of k. So remember, B and Pk is the number of words of length n that contain the pattern P exactly k times. The simplest case is k equal to 0. So we're looking at words of length n that avoid P, that don't contain P as a subsequence. And the nice thing about this is that this value only depends on, of course, n and the length of P. So if P is of length m, then B and P0 is this expression over here. And I'm not going to prove this, but it's a fun exercise which I encourage you to try. Okay. So what I'll talk about is the idea behind the expressions we got for B and Pk for k at least 1. So basically what we did was explicitly construct all the words that have k copies of P. And the way we describe these constructions is by using runs of binary words. So a run in a binary word is a maximal string of consecutive letters that are all equal. Basically, they're the blocks of zeros and ones in the word. So for example, the first run in this word consists of these 3 zeros because I can't really extend it, right? The 0 changes to a 1. So basically wherever the letter changes is where the run breaks. So these first 3 zeros form the first run. Similarly, these 2 ones form the second run because on either side of them are zeros. And that's how you break up a word into runs. Now what I'll do is give an example of how when you're given a pattern P, how can you construct words that contain exactly 2 copies of P. So we'll do that by looking at an example. So here we'll take P to be this pattern 110, 110. Now the first step is choose a run of size 1. So here we'll choose the second run, which is the solitary 0 over there. So it is a run of size 1. And what we'll do is basically just double it. That is, change it to a run of size 2. So that red 0, you place one more red 0 after it. Then of course this word has 2 copies of P. Basically you have to choose all the blue letters and then you have a choice. Okay, should I take the first red 0 or the second red 0? Okay, so we got a word that has 2 copies of P, but this is a very small word, right? We've just added 1 extra letter. So we want longer words as well. And we're basically going to do that by just adding more letters to this word. So now when we do that, see, this word already has 2 copies of P. So if we add more letters, of course, these 2 copies are going to remain. So basically into these slots, we want to add letters in such a way that we don't increase the number of occurrences of P. So for example, in this first slot over here, I can add as many zeros as I want because the first letter of P is a 1. So in my word, how many ever zeros are there in the beginning, that doesn't really matter, because if I am looking for P, I have to look for a 1 first. So if my word starts with a bunch of zeros, that doesn't really play a role. So in this first slot, I can add as many zeros as I want. But I can't really add a 1 there, because if I did have a 1, then I would get a third occurrence, basically by using this purple one rather than the blue one. So in the first slot, I can add as many zeros as I want. Now we'll look at the slot between the 2 red zeros. Here you in fact can't add anything at all, because if I added a 0, again I would get an extra occurrence, basically using the purple 0 rather than either of the red zeros. And even if I added a 1, you can check that you would get a third occurrence. So in this slot between the red zeros, I can't add anything. Then similarly, you can figure out in the other slots what sort of letters can be added. And what can be shown is that this is the only method to construct words that have 2 copies of P. So of course, I just gave an example, but once you write down this method properly, it allows you to obtain this expression for B and P too. So for example, if P has R1 runs of size 1, then this term R1 over here is exactly that, the first thing I said, right? Choose a run of size 1. So this R1 represents that. And then this binomial coefficient is basically a balls and boxes sort of counting of how you can fill up the slots. And we have similar expressions for B and PK for K at most 4. And this idea can probably be used to get expressions for larger values of K, but that would be a bit cumbersome. Okay, so for K equal to 2, you had only one method to construct words, but as K increases, the number of methods increases. And so it gets a bit tedious to check that, okay, all words are constructed from such methods and stuff like that. So maybe one thing to explore is whether there are other ideas. Okay, all the methods that we described looked at words as runs. So is there some other ways to look at binary words that will give nicer expressions for these B and PK? So that could be something to explore. Now our next goal is to look at maximum occurrences and internal zeros. Now what does that mean? So for a given n and p, I'll define m and p to be the maximum number of times that a word of length n can contain p. So basically it's the maximum value of k such that b and pk is non-zero. And a word of length n is called p optimal if the number of occurrences of p is precisely this m and p. That is, it is a word that has as many p's as a word of its length can have. Now our results for m and p are for specific patterns p, that is patterns that have at most 3 runs. So we'll assume p is of this form, like 1 to the I, 0 to the j, 1 to the k. Now what this first point is saying is that you can always find a p optimal word that looks pretty similar, a word that looks like this, 1 to the a, 0 to the b, 1 to the c. And of course, the number of occurrences of p in this word is precisely a choose I into b choose j into c choose k. So that gives us this expression for m and p. What the second point is saying is that if I have a p optimal word of length n, it is pretty easy to find a p optimal word of length n plus 1. So basically, if this 1 to the a, 0 to the b, 1 to the c is p optimal, then either by increasing a or increasing b or increasing c, if I look at one of these 3 words, one of them also has to be p optimal. Okay, so that was the results for m and p. Now we'll go to internal zeros. Now if I look at all words of length n, the number of occurrences of p, the least number of occurrences is of course 0. And it's easy to check that you can always find words that have 0 occurrences of p. So this b and p of 0 is always non-zero. And by definition, the largest number of occurrences of p is m and p. And so this b and p at m and p is also non-zero. But what about these numbers in between? Are there any zeros here? Are there any internal zeros? So pattern p is said to have an internal 0 at n if there is some index between this 0 and m and p, where this b and p of k is 0. Basically, if there is any 0 over here. And again, our results for internal zeros are for patterns that have at most 3 runs. And what we have proved is that if P is an alternating pattern, that is, all runs are of size 1. So it is one of these words over here. If P is alternating, then it does not have any internal zeros at any n greater than equal to 7. So basically, eventually at all integers, there are no internal zeros. And if P is not alternating, then eventually at all integers, it does have an internal zero. In fact, we have specified this basically second to last index, m and p minus 1, is always an internal zero. Okay, so I thought I'll end my talk with a conjecture. So before doing that, I'll have to make a definition. So two patterns P and Q are said to be Wilf equivalent if all these numbers match. That is, B and P of K is equal to B and Q of K for all n and K. Now there are some sort of trivial equivalences. So of course, if Q is equal to P, then of course P and Q are equivalent. But also if Q is the reverse of P, that is, suppose P is 1, 0, 0 and Q is the reverse. So you just read the word from right to left, 0, 0, 1. Then also P and Q are equivalent, because basically if a word has 5 copies of P, the reverse of the word has 5 copies of the reverse of P. So P and its reverse are equivalent. Similarly, P and its complement are also equivalent. By complement, I mean change all zeros to ones and ones to zeros. And for a very similar reason. And also P and its reverse complement. So you reverse the word, then you change all zeros to ones and ones to zeros. So P and its reverse complement are also equivalent. So these are usually called the trivial equivalences. But what we conjecture is that these are the only Wilf equivalences. That is, if P and Q are Wilf equivalent, this is precisely because Q is equal to P, the reverse of P, the complement of P, or the reverse complement of P. Now this upward direction is obvious, that if Q is one of these words, then of course P and Q are Wilf equivalent. But the conjecture states that even the reverse is true. If P and Q are Wilf equivalent, it's precisely because Q is one of these transformations of P. And we have checked this for patterns up to length 13. So yeah, finally, I'll also mention the types of questions we looked at, like internal zeros, maximum occurrences. That was all based on similar questions that were studied for patterns in permutations in this paper by Bona, Sagan, and Vatter. Okay, and usually I like to end my talks with a silly little joke or something. And I thought, okay, I would do something with the subsequences of thank you, but I got a bit lazy, so I'm leaving that as an exercise to the listeners. So with that, I'll end my talk, and thanks for listening.